is that Avinash did it, so probably Avinash should know everything.
Okay.
I was sitting there. I think he should be able to guide you, but most probably you can yourself do it. And did you find out whether you're paying or?
I talked to. I read an email. She actually needed me to send her a form for something else. I haven't sent it back yet. But she said that. What did she say? She might not have actually responded to that. I'll have to ask her again. Because I asked her if I should just go ahead and pay it and then they would reimburse me afterwards. But now that we have more time, then maybe I could just get her to pay it. So, but yeah, that was a couple of days ago. I don't know.
Because it's just that it has to go through some P card, and now I'm not officially part of McNair, right? It was only the summer that I was.
I'm not sure how it works. Yeah. I'm not
I think
sure.
it was only
It's
2
probably
months.
over.
Yeah.
Once the.
So because in the summer, what they did is that they transferred not even to me, to the department, and then department spends it. Then you get it. So,
Okay.
so someone should have that account number. I don't have it.
Okay.
But Dr. Mazumdar has it, but I don't think he can do it either because he's not affiliated with you.
Okay. Yeah. I'll ask
So
her.
yeah, she will tell you most probably what it is. Because that's much more straightforward than all this spending and then getting back.
Yeah.
Especially sometimes when there is tax involved, they don't like that because university gets tax exempted.
Okay.
So if there is a significant tax there, even if it's a small amount, it's accounting, they don't like it.
Right.
So it just creates a problem.
Okay. Yeah, that makes sense.
Okay, half a minute to burden, he's usually on time. And did you decide about what's that, undergraduate?
Oh yeah, I saw your email later
Yeah.
that night, and so
Again, it's up to you. This is Dr. Mazumdar's advice is that usually these are reasonably nice things to do because usually you have to spend money, and that's a measure of how, like if you have attended 3 conferences, that means you must have been research active.
Mhm.
But now that it is free in a sense, you don't have to spend so much money, just the registration is part of it, and McNair and Reach do have that much money. You can actually register for 5 of them and just give a talk
Okay.
and do the necessary attendance.
Right.
And it could help. So that was what Dr. Mazumdar was saying,
Okay.
but you want to think about it. Yeah, it's always a little bit of effort. You can give the same talk and it's a different venue altogether.
Right.
So it's okay to give the same talk.
Okay.
Yeah, think about it. I'm not asking you to do it. It's just an information for you.
Okay.
That's what to do with it.
Yeah. Sounds good.
So let's begin, I think. I did curve your grades at this stage. So since midterm 2, like curve after midterm 2. So this should have been done immediately after midterm 2. I got lazy and did not end up doing that on time. Oh, thanks. What do you do? Here.
Yeah. Rain.
It's right now. Yeah, I hate that part of it. I was telling you're usually on time. Okay. So we just barely started going. So, so this is the curve after midterm 2, which I never ended up doing until now. This is homework 8 is not included yet. I'm in graded homework 8, not graded. Otherwise, everything else is graded. And so this is after the curve. So A, right? Remember the curve factor. So that was 0.25. So before the curve, it was 70. People have 70. This is 98. The highest is after the 6. And it's good to put back. So just to give you a feel for how much this contributes, that's 76. So not every, so this depends on that extra credit, right? So you can have a 5-point increase if you all the, but of course, as you get higher, you don't get so much. So that's a measure of it. And if you're lower, you can get significantly more. But as it goes on statistical basis, usually the extra credit also decreases. Not many people submit extra credit. Anyway, so that should help. And homeworks, not homework 10. It's due Monday. We have midterm 3. The 6th, Friday, and the final exam. So December 11th. That's Friday. Any questions in that? So we were doing a method of images, and we pretty much did most of it, but we want to do a little bit of analysis concerning energy and momentum. So just to remind us what we were doing, this is method of images. And it's a good way of imagining what happens to a charge near a conductor whenever you have a situation to analyze that, even if it's a curved surface, when it is very close to the surface, that curved surface seems very parallel to the charge, and these methods work. And what we have is you have a conductor. So that means conductor. So let's say, let me just explicitly write this is the conductor. Right. And this is vacuum. This means epsilon tends to infinity. And this is epsilon is equal to epsilon naught. Right. That's one way of looking at it. Well, the polarization is very large in here. We also set the electric potential to be equal to 0. That means it is grounded. So this means it's grounded. And which of course means that the electric field will be 0 because it's negative gradient of the potential, which will be 0 inside. So inside a conductor, electric field is always 0. the electric potential need not be zero, it will be constant. But if you choose that to be zero by grounding it, then you have the electric potential also to be zero. If you place a positive charge right next to it, so there's a distance A, let's say, distance A, then this induces a negative charge in here for all practical purposes. This is your plate, that's your positive charge, and there is an image charge which is exactly the same as your positive charge but negative in sign. If it is a negative charge, it would be a positive charge. It is the same distance on both sides, A and A, and the field lines would be as if this was a dipole. Remember, your dipole field is like this. The dotted line means that they would like to go through that, but they don't exist, right? Electric field is zero inside. Inside everywhere it is zero, but you can imagine this to be extending to that. But this is all an abstract concept, right? It's like looking into a mirror. You have an image there, but they don't really exist. So that's the same idea. So these are all images. So what are these quantities? We said that electric potential due to this image configuration is equal to, so we can find this now everywhere, inside and outside. So let me just summarize what it is. It is zero inside, so because it is grounded. Let's see, less than zero. And outside, this is 1/4 pi epsilon naught times there is a charge, the electric potential due to the positive charge, which is x squared, the observation point. So what I mean here is there is an observation point here, right? So it's x, y, and z. And the position of the charge here is 0, 0, A, and this one will be 0, 0, minus A. So the electric potential will be x squared plus y squared plus z minus a the whole square, square root of that. And the other charge is negative. So it is q over. And it is now placed on the other side. So this minus. This is for z greater than z. That's your electric potential. Electric field, we showed, I won't explicitly write that. Electric field is basically the gradient of this potential. But we did point out that this can be written as, since there is a electric field inside is zero, outside is having a mathematical structure. So we can write this as using a Heaviside step function theta of z times a vector field c, which is c is exactly equal to the electric field if it was z was greater than 0. What was the advantage of writing it in this form? That actually allows us to calculate the charge density. Charge density, because of an electric field, is simply the divergence of the electric field. So I take this expression, take a divergence of that, that gives me the charge density. And it turns out that when it hits this step function, there is a charge density that is induced on the surface of the conductor. So we figured out that induced charge density on the surface of the conductor. So this is induced surface charge density on the surface of the conductor. And that's a general statement. So this is x, y, and this is 0 because it is on the surface. In general, if this was a curved conductor, this will be the equation of the surface. So this is on the surface, and that's always equal to the electric field that is right at that point. And in fact, it is simply delta function. This is delta of z. You take the derivative with respect to the step function times epsilon naught times the electric field calculated on the surface. So this is z at that time. If it is on the surface, you might wonder, should I come from the positive or from the negative side? So it should be from the positive side. So limit delta tends to 0. Limit delta tends to 0 plus. So you shift the point a little bit from the surface, there is an electric field, and that electric field actually decides your surface charge density. And I should say delta function shouldn't be there because this is charge density, right? The charge per unit area. So this is giving you the third dimension. I don't have to write that. So it is simply equal to the epsilon naught times electric field. That's really nice because once I know the electric field, I know the charge density that is induced on this. So that means there'll be a lot of negative charges it will pull from the ground, right? That's what we are trying to say. And for our problem, we calculated this, and this comes out to be equal to 2 times, it was a negative, it was negative 2 times A times Q. Q is the positive charge that is inducing the charge, and that's 4 pi. Epsilon naught got cancelled, and we have 1 over square plus y square plus a square. That's 3 by 2. Notice the dimensions. There's an a cube in the denominator. One of the a's in the numerator cancels, so it's charge per unit area. So that's okay. And we also notice that the total charge induced dx times dy. So that's sigma of x, y, 0. That's equal to the total charge induced and that's equal to exactly minus q. So we did this integral last time, and that comes out to be exactly minus q. So now what we have basically is at this stage, with all the analysis, we have electric field, there is a charge out there, and there is few things we can do, right? So this is a charge conductor, and we have charges here. There's more charge at the right next to it, and it goes away, so that's positive charge Q. And this is sigma of xy. And we can ask if there is a charge distribution like this and plus charge, they will feel an attractive force, right? There will also be an energy, right? So what is a force? So what is the force, let's ask? And what is the energy? That's the two things we can do. And it's immediate, right? In principle, it's at least the construction of the problem is very much like we do in elementary physics. We have a charge distribution. We just have to calculate the energy. So let's do that. So let's do the energy first. So it's energy. interaction energy if you want. And the first, how we will do this is we take a small element of the area on the plate, right? And then do the interaction energy between that point and this cube, and then add up. So let's say that is this du, which is.
Could you turn the camera?
Oh, yeah. Thank you. Is that visible?
Yeah, it's good.
Yeah, I can move it a little bit maybe. Oh. Okay, so the energy would be, let's first say that that is a tiny element here. So this is the plate, and that is a tiny element. This is dq. And that's negatively charged, and there is a positive charge here. That's positive charge, and that's distance a. And what will be this distance? If this is a, and this distance in general is, this need not be on the line, right? This is a plate. So it could be anywhere on that x and y. So this is x squared plus y squared in general. Right, that's that arbitrary point in there. And what is dq? First of all, let me write du. So between that particular small element of area, and this will be 1 over 4 pi epsilon naught. Dq times q. So this is q. That's q. That's q. Two charges divided by the distance between them. The distance between them is, let's call this the radius rho. So rho is going to be x squared plus y squared. And phi is tan inverse of y over x, right? This is the plate here. This is the x and y. And any point in there is x comma y. That's your tangent of phi. That's your rho. That's your y. That's your x. This is in the plane. Right. So the volt area element here, dq. So dq would be equal to how much charge there is in a particular area, but charge per unit area is sigma. So dq per unit area, let's say per unit area is dx times dy. So charge per unit area is equal to sigma of xy, 0. So dq over dx dy, that's a small area, will be equal to sigma of xy2. So dq is equal to sigma times dx dy. I'm not writing the xy dependence in there. The sigma itself is, we said, given by that expression. And what's the distance between them? That's this quantity. If this is rho, this is a squared plus rho squared. That's your a squared plus rho squared. Okay, that's the energy element between this point and that point. And we are to add up all these quantities for the whole plate, which means to say that we have to do an integral. But before that, let me replace the dq with dx dy. So this is 1 over 4 pi epsilon naught. And dq is sigma dx dy, and that is a q divided by a square plus rho square. Is that clear? The equations? But I know the expression for sigma. Let me put that in. So I have 1 over 4 pi epsilon naught. In fact, let me pull the q in here. And there is a sigma, which is minus sign. So there's a minus sign. And this is 2a cubed over 4 pi times 1 over x squared plus y squared plus a squared. Now the whole thing 3 by 2. That's your sigma. That's just sigma. And we have dx dy divided by a squared plus rho squared. Is that clear? But rho square is x squared plus y squared, so I can actually write this as the same quantities. Cool. So basically, if we want to calculate the total energy, is equal to the integration over the whole plate of du. That's all I have to do. Basically, this is for one tiny element. Keep adding that for each element on that plate. That's a physical interpretation. But du is this. So this is minus. So I put in all the terms outside. So it is. Maybe I can write this as q square over 4 pi epsilon naught. Right, q square over 4 pi epsilon naught 2a over 4 pi. So that's 2a over 4 pi. So we go away. And I have the integrals, which is minus infinity to plus infinity dx minus infinity to plus infinity dy. And there is a 3 over 2 of this. There is a 1 over 2 of this. These two are the same, right? Rho square is nothing but x square plus y square. So that's the same. So these two factors are the same. 3 by 2 plus 1 by 2 is 2. So that's the same as x square plus y square plus a square. And instead of being 3 by 2, it's a factor of 2. Correct? That's nice. Dx dy, remember in polar coordinates is dx dy. In polar coordinates is rho d rho times d phi. In fact, it should be d rho times rho d phi. And rho goes from 0 to infinity. Pi goes from 0 to 2 pi. So I can do this integral apparently now. This is q square 2a over 4 pi. And this is 0 to infinity rho d rho. And 0 to 2 pi d phi. And this is 1 over rho square plus a square, and that's a square. There is no phi integral here. So this is actually equal to 2 pi. And that 2 pi actually multiplies this with 2 and 4 pi cancels out. So that's 4 of that 4 pi and 2 pi cancel out. And we have minus q squared over 4 pi epsilon naught. Now there's just a factor of a remaining now, right in the front. But there are 2 distances here and 4 distances in the denominator. So it's 0 to infinity rho d rho over rho square plus a square. 3 distances in the numerator, 4 distances in the numerator. So dimensionally, that's 1 over length, which is the dimensions of energy, right? Energy should be charge over length, and then it's 4 pi epsilon naught. That integral can be done. We can substitute rho square plus a square is equal to, let's say just, let's just say t square. Then 2 times rho d rho is equal to 2 times t dt. The 2 cancels out. So rho d rho is t dt. So that's equal to okay. The limits become when rho is equal to 0, t is equal to a. And when rho is equal to infinity, t is going to be large. So that's a to infinity. Rho times d rho is nothing but t times dt divided by rho square plus a square is t square. That makes it a t raised to 4. That's nice. So that's t cubed, right? So that's the same as minus q square over 4 pi epsilon naught times a. And this is 1 over t cubed. The integral will be t raised to minus 3 yeah, minus 3 plus 1 divided by whatever is the power there, so that's minus 2. Right? And that's evaluated at t equal to infinity and t equal to a, which is the same as minus q square over 4 pi epsilon naught. There's a factor of a. When I evaluate this at infinity, so this is, notice this whole thing is actually minus 1 over 2t squared. But t raised to minus 3 plus 1 is minus 2 t squared, and there's already a minus 2, so that's minus 2 squared. So that's either way at infinity it is 0. And at a, it is plus 1 over 2a squared. That's good. So one of the a's cancel out. And what we have is minus 1 over 4 pi epsilon naught. Q, let me write this in this following form. So there is Q plus Q, that's your original charge, minus Q, which is the image charge, divided by the 2 times A, which is actually the distance between the images. So we didn't have to do all this integral if we had realized that, oh, this is just going to be the image and the charge, which we sort of suspected, but you never know. So that's exactly the energy between the charge and the image charge. So this is the interaction energy between the charge and its image. So remember again, so this is your conducting plate. You have positive charge Q here with a distance A, and there is a negative charge here, so that's negative Q, which is again the same distance A. But if these two are interacting, this distance is 2 times A. Right? Charge times 2 times A. So that's it. Next time you have to do the interaction energy between a charge and a conducting plate, we forget the plate, introduce the conductor, and just use this form. Very straightforward. You don't have to do all this integrals. So that's the power of method of images. When it is curved surfaces, it is not exactly like parallel plates. There are more better prescriptions, but in general, this is how it works. It's just geometry comes in more factors comes into picture. That's okay. So that's energy. What about the force? Right. So one might be confused as to does that really work with the force? Because remember, if there is a energy, force could be the derivative of the distance between them. But which distance do you talk about? Like, is it this distance that we're talking about when you say that the force is a gradient of So this could be a confusion. So force is d by dA. So you move a charge a little bit with respect to the potential energy, right? But which distance are we talking about? Is it the distance between the charge and the plate, or is it the charge and the image? Because if you move this a little bit, the image also moves a little bit. So that's a question that could ask, and that actually allows just at least once verify which distance actually is important. But again, do this calculation for the force, right? Even though eventually whatever we learn will be very simple, we have to do this calculation again for the force. So let's do that. It'll go very much similar. Most of the representation for the integral will be the same, except that now this will be the force. So now, change the board. So now we do the force on this plate. So if there is a small element dq here, and that's your positive charge, we have to ask what is the force exerted by this charge element, and we know that it's going to be an attractive force, which will be in this direction. So that will be your dF, which is a vector now. But we also know that symmetrically speaking, this will have a component in here. So this component will get cancelled by a corresponding component from the bottom. So it's only the horizontal component that survives, and it is the horizontal component is this. So dF would be equal to, so dF in the x direction, right? So dF in the x direction would be equal to the actual force between them. So that's -1 over, or dq will bring in the minus sign, right? So this is 1 over 4 pi epsilon naught dq q over the distance between them. So this is a, that's rho. That's rho square plus a square, square root. That's that hypotenuse, and then you have to square it. Right? Force has a square in that. But that's just the magnitude of the force. I have to get a cosine theta in it. That's cosine theta. But cosine theta is in itself equal to, cosine theta is a over the a square plus rho square. Right. So this is already having a factor of rho square plus a square plus one of them. So that makes it 3 by 2, I suppose. So the same idea, we again integrate. So the total force F, because everything will cancel. Now I don't have to worry about the x component. So this will be magnitude of the, let's say this is force. Right? So this will be equal to, it'll be in the I hat direction, and it'll come out to be negative because this dq is going to be negative. This is 1 over, integrate now. This is integral minus infinity to plus infinity dx, the same as what we did there. dy minus infinity to plus infinity. And then there is 1 over 4 pi epsilon naught. dq is d sigma, sigma times dx dy. So sigma was as a minus sign, q a q over 4 pi times 1 over rho square plus a square, and that's 3 by q. So that whole thing is sigma. So sigma dx dy is dq. Still there is a q over rho square plus a square. square root of that is rho square plus a square, and there is a cosine theta, so let's also have a over a square plus rho square. That's 1/2. So this is coming from cosine theta, that's coming from the force, and that's coming from sigma. So that's coming from sigma. So check on me. I think that's all correct. Right? And minus sign has been pulled out all the way to the left. Okay, so this is equal to minus I hat. That is q square there divided by 4 pi epsilon naught. And there will be a factor of 2 pi coming in from the phi integral. So I pulled this out, minus I out, 2 pi, 4 pi, that cancels out, and that is an a square. So this is a square. So I can write this as 2 pi coming from the phi integral, and that is a 4 pi. Right, so I collect all of that in that way. So this is 0, infinity, rho, d rho, over how many powers here? 3/2 plus 1/2, that's a 2, and then a 3. The rho square plus a square, and this is this time 3. I jumped a few steps, but I think since we did pretty much in detail there, that's good. Let's check the dimensions at this stage. There are 4 distances in the numerator, 6 distances in the denominator. So that is a 1 over length square, which is what should be. Force is charge square per length square. So 4 pi cancels out. So we can again substitute this as rho square plus a square is t square. Do the same thing. So it's minus I hat q square over 4 pi epsilon naught. This cancels out, a square, and we have rho d rho is equal to t dt, right? As we did last time. So it's a to infinity, rho d rho is t dt over t square, so it's t raised to 6. So that's equal to minus I hat, let me write once more, a square. This is integral of a to infinity dt over t raised to 5. Hopefully this all out. So this is equal to minus I hat q square over 4 pi epsilon naught a square times what is the integral minus in. So let's do that separately here. So that's a to infinity dt over t raised to 5. So that's equal to t raised to minus 5 plus 1 divided by minus 4. Correct. So that's the same as, and it has to be evaluated at the limits, right? A to infinity. That's the same as minus 1 over 4 t raised to 4, infinity and a. That's equal to 0 plus, actually, minus and a minus catch up. So that's 4a 4. But when substituted, gives q square over 4 pi epsilon naught. That is an a square in the numerator, and that is a 4a raised to 4 in the denominator. That's actually good, because now we can interpret this as I hat times, let me write the plus 4 pi epsilon naught in the front. That is plus q, that is a minus q, and then that's 2 times a squared. So it is the distance between the image and the charge that comes in. So this is again a force between the charge and the image. And if you want to interpret this as a derivative of a quantity, so the way we should look at this is that this is negative gradient, or let me write this as force itself. So F is equal to minus 1 over 4 pi epsilon naught q square over 2a square. And if I were to take this in the same way with respect to energy, so this is q square over 2a, and you learn that the force is equal to negative d by d with respect to 2a, right? Not the distance between the plate and the charge, it is the distance between the image and the charge. Why? Because when we move this, so the force has to do with minimization of energy, right? When I move this, the induced charge is also changing. So the plate is actually changing. It depends on this A. In fact, there is an image charge. That's what it is sensitive to. So that's what it is. Force is decided by a derivative with respect to 2A. More explicitly, if you were to change the induced charge itself, then also you can get that expression. So that should explain how to deal with at least a simple form of conductors. And this generalizes. I mean, I can immediately do this for a sphere or in general for any curved conductors. And next time, actually, we will try to get this. If we have a conductor, how do we solve for its field in general? Like just to begin with, how do you solve these differential equations? So let's switch over to that. So as of now, I will stop with this. Any questions? Yes.
When you evaluate the integral from 1 over t to the fifth, wouldn't you have a negative sign that canceled with yours?
This one?
No, in the last line here, you have minus I hat starting all the way at the left.
Here.
Yeah, and then if you start to the left.
This one? Here.
So
that's negative.
But then the t to the minus 5 integral would also have a negative sign.
No, right? This is positive, right? So maybe I didn't write this here, right? So
already evaluated, yeah.
Right. So I evaluated it here, so I think that this shouldn't be there. I meant to write directly there, so that's wrong. Correct. So I wanted to write this and write the integral, but then I didn't realize.
Okay.
Yeah. Okay. So it is positive. The integral comes out positive because again this is negative, but when I evaluated it, it's at the lower limit. So the lower limit has to be subtracted. That's positive. So yeah, it all fits in very well. It's necessary. Otherwise, if you change the sign, it is not okay. And then it doesn't match with this. So it has to. But for the first time, one has to confirm that. Yeah. Good.
Quick question.
Yes.
I remember at the beginning you wrote down d f of x. If it was f of y, would that be a different?
There is an f of y, this one, that's exactly correct. Then it will be sine of theta.
Okay. And then for
What happened to that? Oh, what happened to f of z?
does f of z?
F of z doesn't come in, right? This is a force. Where is z? Actually, I said x, this should be z, right? This should be z. Because this is actually z.
If it was f of y, would the final answer be like j hat?
That's exactly correct.
Okay.
Yeah. But point is that this is a plate, right? For every x in the upward direction, there is an x in the bottom direction, y, they all cancel out.
Okay.
So using symmetry arguments, we say that, oh, we don't have to worry about that. So we just threw away all of that.
Okay.
But that's a good analysis, yeah. So I can, like, these are all good questions for the exam, right? I can ask you, okay, show that this is actually really zero for the y for this vertical directions. Okay, good.